Welcome back. In this lecture, we are going to continue on dense subsets of continuous functions. We had proved the Stone-Weierstrass theorem in the previous lectures. In this section, we are going to restrict our attention to periodic continuous functions and approximation by trigonometric polynomials, which naturally leads to Fourier series and so on. So let's start with what are trigonometric polynomials. So let's say p hash n minus pi denote the space of all 2 pi periodic trigonometric polynomials of degree n. Okay, so it has this form. So this is a degree n polynomial of trigonometric functions. So here in this notation, it basically means that the function is defined from on the domain minus pi to pi, and beyond that anyway it's 2 pi periodic. So the value at minus pi is same as the value at pi here. Okay, and this n represents the degree, this hash here as a subscript represents the periodicity. So it's periodic functions of n degree defined on this. So in the real variable trigonometric polynomials are usually n degree trigonometric polynomials are given by this form, right? So here you see the k sums from 0 to n, and here the k sums from 1 to n. So basically you have all cos k theta, sin k theta. Now one can observe immediately that in fact you can verify that will form a vector space and so on, the space of 2 pi periodic functions. And you can actually observe that 1 cos k theta and sin k theta, the k equal to 0 corresponds to the constant function here. Okay, so 1 cos k theta and sin k theta actually generates this. So you can, any element here can be generated by these elements here, which actually where k runs from 1 to n means you actually have 2n plus 1 elements here. So this has a dimension of 2n plus 1. So because there is a n element here, there's an n element here, 2n total and plus 1. Okay, and the space of all 2 pi periodic trigonometric polynomials of any degree can be seen as union of all n degrees. So this is the space of all 2 pi periodic trigonometric polynomials. So that's union over all possible degrees. Okay, and each of this you see, as we have said, is of dimension 2n plus 1. So this is the space of all 2 pi periodic trigonometric polynomials. So from the Stone-Weierstrass theorem of the complex version that we already proved, as a corollary to that, we can prove this density of the complex valued 2 pi periodic trigonometric polynomials in 2 pi periodic complex valued continuous functions. So this notation means it's all continuous functions from minus pi to pi which are complex valued and they are periodic. The period is 2 pi. So the trigonometric 2 pi periodic, so the trigonometric polynomials are dense, which are complex valued, are dense in complex valued continuous functions which are 2 pi periodic. This is a very simple corollary of the Stone-Weierstrass theorem complex version that we proved. So this is just a comment to tell you that, for instance, the density is not valid for non-periodic functions. So here you don't, I mean, in the uniform norm, in the supremum norm, you cannot replace this by removing the periodicity. So it is a class of all continuous functions. So this is not valid. A simple example one is that if you take the identity map, right, that f(x) going to x, here it's not periodic, right, because the value of x at minus pi is pi, which is not 2 pi periodic at all. But if you have done some Fourier series, you would have seen that you can write down, you can extend it periodically by as a saw function or something. It's called a saw function, where you do a periodic extension of this, where at pi you impose the value at minus pi and so on. That's a different thing, but as such you cannot approximate this function in the closed interval minus pi pi by a trigonometric polynomial. Another way of seeing this is that actually the 2 pi periodic trigonometric polynomials do not separate points. That's one of the hypotheses that you need for density, what we have seen in the previous lecture. So that is also not satisfied by this. It will not separate points. Right, and that is obvious, right? Because if you take minus pi pi, because of the 2 pi periodicity, the value at pi and minus pi will be same. So there is no function which will take different values on these 2 points when you have a 2 pi periodicity. So that's why it doesn't separate points. So what is the proof of this trigonometric polynomial density in 2 pi periodic continuous functions is that you first map this minus pi to pi to the unit circle in the complex plane, right? You can do this map, right, from theta going to e power I theta, which will give you this unit circle, right? And that's a compact set in C. Okay, that's a compact set in C, and that is actually a map. That's actually a map which from minus pi to pi to t. So every continuous 2 pi periodic continuous function can be seen as a continuous function on the unit circle. So here there is no periodicity because it's taken care of, right? So every 2 pi periodic complex valued function can be uniquely associated with a continuous function on the unit circle. Now for each 2 pi periodic function which is complex valued, uh, you can associate, I mean, you can sorry, yeah, for each f in this here, you can associate a continuous function on the unit circle by defining it like this, right? So for f in this, you define f star, which is on the unit circle, defined like this as f star, because any element on the unit circle is ei theta. So f star of ei theta is f of theta. Okay, so you have this association, which is a bijection, certainly continuous bijection. All that you can show. If you don't know, please try doing it as an exercise. Okay, so you have this bijection between every function here can be associated with some function here, and that map is a continuous bijection. Okay, so you need to verify that whenever f is continuous, then f star that you have defined is also continuous, and so on. Okay, so do it as an exercise. Okay, now I don't think the composition of function. Whatever, try doing this as an exercise. So whenever, so what we are saying is, suppose you take an element here, you need to show that this association f star is an element here, which means you need to show that f star is a map from t to c, which is obvious. You need to show that it's also a continuous function on t, which will also which will follow from the fact that f is continuous. So once you have that, then you take the subspace which is 2 pi periodic uh, 2 pi periodic functions of I think there is a this has to be yeah, this is not x, this x is some typo here. So what we are taking is, we are taking this one, p hash minus pi pi. Okay, so p hash minus pi pi is what we are taking here, which is actually a subset in here, right, in this. So we are just taking this one, all functions in that image there. So you take all periodic functions on T to C, which will be a subspace of C from T to C, and they satisfy the hypothesis of the complex Stone-Weierstrass theorem version, right? So these are all the trigonometric functions from T to C. So, and and it will also satisfy to check all the hypotheses of complex Stone-Weierstrass theorem. Everything else is easy to check. The separation property is also valid, because if you take any two elements on the unit circle, the image of this function, that is f theta is equal to I theta, which is f star, which will actually be an identity function. F star is actually an identity function. So f star of z will actually go to z, and f star of w will actually go to w. So if you choose two distinct z and w, the image is also distinct. So this will automatically be satisfied. So this is a separation property which will be satisfied by p hash of tc. So this subspace will satisfy all the hypotheses of Stone-Weierstrass theorem. So should be dense in CTC. Okay. So this shows that all trigonometric polynomials, complex valued, is dense in the space of of 2π periodic continuous functions. Now this result is also true for real. So here, whatever we have said here in this statement here is actually also true when if you take real valued function with 2π periodicity and so on. But it needs a bit more work to do. There are other, there is this Fourier's theorem which you prove, and using that density you show that it's dense and so on. Okay, so you can look it up. We will see whether we will do it in the later lectures as well. So this kind of proves, so we have seen the polynomial approximation of continuous functions. Now we have seen the trigonometric approximation of 2π periodic functions and so on. So in the case of periodic functions, you see we are only proving the density in the 2π periodicity function, but not in the class of all continuous functions. And that I have already given one example here, like the identity function and so on. So it's kind of not true, and it fails because of the uniform norm. And that is precisely what you do in a Fourier series. What Fourier series tells you that you can actually do this trigonometric approximation not in the uniform norm, but in the L2 norm. If you do it in the L2 norm, then you can actually approximate even a non-periodic function and even continuous functions and so on. All these continuous functions or even L2 functions can be approximated in the L2 norm by trigonometric polynomials. This is what the Fourier series subject tells you. If you do a Fourier series course, you would have seen that. So that takes us to the definition of Fourier series. We have already shown a kind of Fourier series for 2π periodic functions when we did the Laurent series and so on, right? So as an application of Laurent series, we had seen that 2π periodic functions, complex value. Here, a complex value admit Fourier series and so on. This is a much more general. So for any L1 functions, that is integrable functions, you can define its Fourier series as this form. This is precisely the cos and sine terms, where this f hat n, is called the Fourier coefficient, which is defined as the L2 inner product of f and e power minus inx. Okay, this is the definition of Fourier series. So this is how you take any L1 function, you define its Fourier coefficient using 7.2. So you define this. This will be fine if you are talking, you are dealing with an L1 function here. So you will get some f hat n, and using this f hat n, this you can do for each n here. So using this f hat n, you write down the series. So once you have that series, that is called the Fourier series of the f that you started with. But it is not necessary that the Fourier series that you write down will always converge. And even if it converges, it is not necessary that it will converge to the f that you started with, right? And when you say converge, in what sense? Pointwise or uniform? And even if they converge in some sense, pointwise or uniform, it need not converge to the given function f. And whether it converges for all points x in the domain or some points, all this can happen. All these variations can happen. And the subject of Fourier series is precisely to understand these different cases. So in this, by the end of this talk, we are going to show to you that there is a large collection of functions and there is a large collection of points in the domain where this series will not converge. Forget about converging to f. It just diverges, right? So it kind of goes to infinity. It does not converge, and that happens for a large collection of functions and a large collection of points. That's what is the aim of this lecture. So by the end of this lecture, we will see uh, proof of that this Fourier series need not converge for a large collection. So to understand that, let's start with the notion of what is called the Dirichlet kernel. So this is naturally associated to the Fourier series. So how does this Dirichlet kernel appear is a point. So if you take this Fourier series is a series, right? And you know from series, you can talk of the convergence of a series by looking at its partial sums. So that's what we are doing here. This SMF is the partial sum of the Fourier series corresponding to f that we have written down, right? And whenever these partial sums converge, the Fourier series will converge. That's what it means. So this is the partial sum. So this is the mth truncation, right? So now using the formula for f hat n, which is the Fourier coefficient, which was the inner product between f and e power minus I n x. So using that formula, we have this relation. Okay. So the partial sums can be given in this form, in this integral form as well. And whatever you have within the square brackets is precisely what is called the Dirichlet kernel. The Dirichlet kernel DMS is precisely what you have here. This is what is called the Dirichlet kernel, and you can think of the Fourier partial sums as a convolution of the function f with Dirichlet kernel. So that is how the Dirichlet kernel naturally appears with the Fourier series. So Dirichlet kernel is what you need to convolve the function f with to obtain the uh, Fourier partial sums. Okay. So, so we have in this slide what we have done is just rewritten the Fourier partial sums in some convolution form. Okay, where this dm is called the Dirichlet kernel. So now we prove a property of the Dirichlet kernel. We basically say that for all m, the value of the Dirichlet kernel is this, depending on whether s is 2k, I mean it's a multiple of, I mean it's an even multiple of pi or not an even multiple of pi. Depending on that, you have values. So that's the purpose of this proof, and the integral of the Dirichlet kernel is 1 from minus pi to pi. I mean integral divided by 2 pi. So integral is actually 2 pi. So if you normalize it, you get this as 1. So to prove this, we observe that we know this property that ei 2k pi is 1 for every non-zero integer and for every whole number, right? Every whole number, this is true, this is 1. So you compute dm of 2k pi where s is 2k pi's and use this definition here, right? You use 2k pi here, so it's 2nk pi, right? And that we know is 1. So if you sum them, you get 2m plus 1. right? So you have that many terms here, right? Minus m, and the 0 term. So if you have 2m plus 1 terms here, so you get 2m plus 1. So we have verified this case here. Now when s is not 2k pi, then you know that EIS minus 1 is not equal to 0. Why? Because s is an element from minus pi to pi. If you notice, that is for the domain, right? So, I mean, s can come from R, but you have this, so whenever s is not 2k pi, right? So EIS is not equal to 1. Okay, so there is nothing to do with minus pi to pi, sorry. So when s is not 2k pi, because these are precisely the points where where this exponential becomes 1. So for any other s, this is never 1. So EIS is not, so minus 1 is not equal to 0 always. So you multiply this non-zero quantity with the Dirichlet kernel, and if you rewrite it using the definition of the Dirichlet kernel, you get this. Okay, and this becomes this. In this sum, you will have only the mth, because it's like a telescopic sum, right? You can cancel out. If you expand this sum, you can cancel out terms, and what remains is this first term and the first term and the last term and so on. So that's what remains here. Okay, so this quantity is precisely this. Now you multiply both sides by e minus is over 2, so you get this. So this is just a computation that you need to do. So if you multiply in this e power minus is by 2, you precisely get the left hand side becomes this and the right hand side becomes this. And this is precisely the result that you want here, because this is just e power I minus e power minus I. What will remain is the imaginary part of this thing, which is the sine part there, and this again sine part there, which will come down here as a denominator. So what you will have is precisely this. Okay, so that's what we need to. So we have proved what we started with. What remains to prove is this integral. This integral is 1. So for that, you start with this 1 over 2 pi integral of this. By definition of dm, you can write it as sum of this. Now this integral is whenever you have n equal to 0, you get 2 pi for every other. So for every other non-zero n here, you actually have this to be 0. So in this integral, for each m sum here, the n equal to 0 case survives. All non-zero n's here becomes 0. So what remains is, so if you have integral of constant function, 2 pi cancels out. So what you have is 1. Okay, so these are some simple things. So we have shown this property of Dirichlet kernel, that dm has this value and the integral of dm is 1. Okay, so I will leave this as an exercise for you to check, that show that this Dirichlet kernel for each fixed m is actually an even function and is a 2 pi periodic function, which is why I was saying there, and though we took it as a domain of R here, it actually becomes a 2 pi periodic function. You can see that from here. So, and you also show that dm is a continuous function. Okay, all these are easy to show. Okay, so now we'll prove another property about the Dirichlet kernel, is that the limit of the integral as m goes to infinity is diverges. Okay, so this is another property that we would need. So let's prove that. So recall this property that mod of sin s is always less than or equal to mod s, right? This is something uh, which we actually know that sin theta or theta limit theta goes to something is actually 1, right? So this is the property which we know about sine. So we are going to use this for that. So you start with this integral. Okay. So start with this integral, and we have already given you an exercise that dm is an even function. So because it's an even function, this integral becomes 2 times integral over 0 to pi, right? Because in even function you can write it like this. It's 2 times of the one part. Now we have already shown this dm value of that is this, and why? Because s is now between 0 and pi. So s is not 2k pi, it's not a even multiple of pi. So s is going to lie between 0 and pi, and for this range of s, the value of dms is precisely this, right? That's what we have shown already. So now we use this property here. So from this property I know that 1 over mod of sine s is 1 over s. So in this case s is s over 2. So this is greater than or equal to s over 2, and that 2 goes here with this 2 becomes 4. Okay. Now you write this this integral 0 to pi as I mean sorry. So what you do, you introduce a change of variable here, right? You introduce t to be m plus half s, and you do a change of variable here, you will have a change in the limits of the integration. That's what we have done here, just a change of variable. Now you write this integral 0 to m plus half pi into intervals of uh, length 1. Okay, so here between n minus 1 to n, right? So it is of n minus 1 plus 1, right? So plus 1 is n, so it's all of interval. I mean interval of length 1. So you can write this integral as summation over smaller parts of intervals, right? And the last part, which is from m to m plus 1, which has a root only half part, I mean, so m to m plus half pi. So this is the last part. Okay. So this is from n equal to 1, which is 0. So it's basically 0 to uh, 0 to pi, and pi to 2 pi, and so on and so forth. After m pi, you don't have m plus 1 pi here, so you go up to m plus half pi. Okay. That's what we have just split this integral into some finite number of integrals. Okay. So now this quantity is a positive quantity, right? Whatever is here is a positive quantity. So this integral is a positive integral. So this is something plus positive. So whatever you have here is actually bigger than this first quantity because you are adding a positive quantity. So what you have here is bigger than this quantity, which is the first part here. So we throw away this with this inequality sign. And whatever we have here, here we have used this fact that t is less than n pi. So 1 over t is greater than 1 over n pi, and that's what we have used here, is greater than 1 over n pi. So now this is this 1 over pi, 1 over n pi comes out here. So you have this integral becoming this integral over this, and this sum over all these quantities, different intervals, is actually 0 to pi. That is how we started and split it, right? So this is integral over 0 to pi of sine t, and mod doesn't make a difference here because sine is anyway positive in this range. And this is precisely 8 over pi by summation 1 over n. Okay, so Now as m goes to infinity, what you have here is a harmonic series which diverges. So as limit of m goes to infinity, this side diverges and this side is a smaller quantity than this side, so this side also diverges, and this is what we wanted to prove, that in the limit this diverges. Okay, so now using all that we have said, uh, we can show a property that if you take the space of all continuous functions to the supremum norm, okay, on minus pi to pi. So here see, I know no longer we have the restriction of 2 pi, but we are not showing you the exact density, but we're showing some property of Fourier series of continuous functions. So if you take in the space of continuous functions with the supremum norm from minus pi to pi, then you define this linear functional Tn from this x to r. It's a linear functional. How do you define it? It is the value of the partial sums of the Fourier series evaluated at 0. Okay. So we have defined this in the some time back, right? So there, wherever you had s, put s equal to 0. Basically, the exponential you will have 0. So what you will left with is just the summation over. So just to show it to you here. Yeah, here. If you see, if you put t equal to 0, what you get, if you put t equal to 0 here, you get this is e power 0, which is 1. So what you get is just summation over the Fourier coefficients. Okay, that is what t equal to 0 corresponds to. So that's what that theorem is talking about. So if you define this linear map as the value of the Fourier partial sum, n partial sum evaluated at 0. So that is Tn. So for each f, you have a corresponding Fourier series, and the truncated at n evaluated at 0, that is a map Tn. Okay. So then this theorem tells you that if this linear function, if you take this linear function is bounded. It's a bounded linear function. That's what this theorem tells you. And the norm of that operator or that linear functional is given in terms of the L1 norm of the Dirichlet kernel, basically. The norm of Tn is the L1 norm of the Dirichlet kernel. So to prove this, let's start with the definition. So Tnf by definition is Snf0, and this by definition, what we have already shown, is 1 over 2 pi, the convolution with the Dirichlet kernel, but now evaluated at 0. So this is what you will have. Okay, and this is precisely fx dnx ds. So you right. So earlier you had dnx minus y or something as a convolution. Now it becomes the uh, with evaluated at 0. It is just the inner product between f and the Dirichlet kernel. So Tnf is precisely this inner product of f and the Dirichlet kernel. Now you take mod both sides, so then you get mod Tn. So you take mod here and mod here. So what you get is precisely mod of this is less than or equal to mod of the Dirichlet kernel here, and the because f is a continuous function on a compact set, right, or closed interval, closed bounded interval minus pi to pi. So this you can take the supremum over all the points. So this is the sup norm of f which comes out. So you have this inequality for mod T and f, right? And what we want is the norm of Tn. And norm of Tn, you know, is norm of Tn is supremum over all f in the space, f non-zero f in the space, where mod Tnf divided by norm of f. So that's what you, and so from here we actually say that mod Tnf less than or equal to 1 over t by this, right? I basically brought this norm infinity here, right? And this taking supremum over all f will still be less than or equal to this, so you have this inequality. But what we need to show is the equality, right? Not the inequality. So we need to show the equality, we shall construct a sequence of continuous functions which converge converges to the equality case. So we just show that the this upper bound is achieved. Then we write it's equality. So for that, for each fixed n, you look at the set of all points minus 5 to 5, where the Dirichlet kernel is non-negative. So that is your set En. So all those points where Dn is non-negative, that is your set En. So Dn restricted to En is positive. Okay. So once you have En, you define this function Fm as 1 minus m times the distance of x from En. Okay. And similar divided by 1 plus m dn. So this is the definition that we are giving this definition for Fm. For each m, you can do this. Now you can observe immediately from the dsn. You know this is the metric, right? This is a metric in that space, which is actually in this case. This is the real metric here, right? Because the En is a subspace of R. So it's not subspace; it's a subset of R. And this is the usual metric that you give in R. Okay. So Fmx is this. So you see that whenever x belongs to, suppose x belongs to En, this distance is 0, because, right, and this distance is 0. So what you're left with is 1. So whenever x belongs to En, the value is 1. Whenever x is in the En complement, you have that value. So Fm has this value. And Fm is a sequence of continuous functions from minus pi to pi. That's by definition, right? So Fm is defined for all elements from minus pi to pi. Okay, and it's a continuous function. By the way we have defined, it's a continuous function, right? Because we have already shown in some previous lecture, at least I think I gave it as an exercise also, that this is a uniformly continuous function and so on. Okay, so in exercise 19, I can show it here. So we had done this in a previous lecture, that in a metric space, whenever you have the distance function, this is not yeah, something, yeah, here, right? We have the uniform continuity of this function. So by that continuity, you have the you have the continuity there. Okay, so where are we? Yeah, proof of three orders, right? Yeah, yeah. So we have a sequence of continuous functions from minus pi to pi. Okay, you can we have already shown this, but you can verify it for yourself that they are continuous functions, just sequence. So now, and the norm of each Fm is less than 1, right? Because whenever x belongs to En, it's anyway 1, the value is 1. For other thing, it's less than 1 because of this property that 1 minus m dxn is always less than or equal to this. So Fm was defined as a quotient of this, so it's always less than or equal to 1. Okay, so this is less than 1 always. And for all x belonging to En, because the value is always 1, it converges, Fmx converges to 1 for all x in En. And when x is in En complement, it always converges to the value minus 1. That you can verify immediately from this fact that the way you hear 1 over m minus d, 1 over m plus d. So when m goes to infinity, the first term, both numerator and denominator, will go to 0. So what remains is this. This is independent of m and with a minus sign, so it's going to be minus 1. Okay, so when x belongs to En complement, Fmx goes to minus 1. Therefore, by the dominated convergence theorem, right? So you have a pointwise convergence here and so on. So by the dominated convergence theorem, and it's also dominated here, right? So limit of m going to infinity t n fm is precisely limit of m going to this. This is by the definition of what we have already shown here. Here, whatever we have shown here, Tn Fm is Fm Dn, right? So you put Fm here. So that's what you have here. So limit of this is limit of that. Okay. And then if you split in En complement, En and En complement, in En Fm is 1, so this interval becomes this. And in En complement, it converges to -1. So this, as limit m goes to infinity, this is minus of this. Okay, so when you apply limit to this, you get this, right? Basically, we have swapped the integral and the limit here. So this limit is now 1 over 2 pi integral minus by the mod dn now, and this is precisely what we needed to prove, right? Right? What we have shown here, the less than or equal to, we need to obtain a sequence of functions where the equality is achieved, and that's what we have proved. That we have found a sequence where it attains the value. So you actually have the equality in this inequality here. Okay. So norm of Tn is that quantity, this quantity. That is L1 norm of the Dirichlet kernel. Okay. So now we are ready to prove the divergence of, that is, the Fourier series diverges in a very large class or large collection. So you see the C minus, the space of all continuous functions from, real value continuous functions on minus pi to pi is actually a complete, it's a complete norm space, right? It's a Banach space, right? And the norm is the usual supremum norm or uniform norm, and it's complete in that norm. We have already seen that. So it's a Banach space. Now you consider this. Um, so, so you consider the subcollection of functions in the x star. What is x star? X star is the continuous dual. So x star is the set of all continuous linear functionals on x, right? So you take a subfamily. So you take a subcollection of x star, and now what is that? What is there in the collection? That collection is all these maps Tn such that supremum of n Tn is infinity. Okay, so you take this collection of family in the dual of x, right, and such that supremum of n norm Tn is equal to infinity. Okay, so we have already done what is called the bare category theorem. When we did the bare category theorem, we had also done the uniform boundedness principle, and the um, vector space version of that is what is called the Banach-Steinhaus theorem, right? Where either you use uniform orderedness principle the way we have done in the previous lecture, one of the lecture, and the consequence of that is the Banach-Steinhaus theorem, right? Which tells you about when you have a pointwise boundedness, then there is a uniform boundedness under some condition. So we are going to use that result. Okay. So you take this subcollection of all Tn such that supremum of n Tn is equal to infinity. So with the uniform boundedness principle that uh, we have already shown, there is a dense G delta set. Let's call it G0 in X, such that the supremum n of T and F, norm T and F, is equal to also infinity. So suppose this was not the case, then it will contradict the uniform boundedness principle. That's how you choose this. So you see here, this is supremum over the norm of Tn. This is pointwise supremum. For every f, you take T and f. supremum over norm Tn f. So if supremum of Tn is infinity, like see the other way, suppose these were all finite, then the uniform modulus principle tells you that this will also be finite. So when this is infinity, so as a corollary we did for the uniform modulus theorem, let me just show you there itself. So you see, if you have a complete metric space and if you have a subfamily of space of continuous functions, right, where x2 are, then one of these two will happen. Either supremum of this is infinity for all x in some g delta subset of x, or there is an m and r such that this happens. This is what we have proved some time back in a lecture, right? This is exactly what we proved. So what's happening in our case now is this, because we started with some supremum of something to be infinity, so which means that this has to be infinity for all. So in this case, the x is the little f and f is the t in our case now. So this is the capital T here, and these x's are the little f's. So there is a G delta set such that for all f in the G delta f, something happens. So that's what we are trying to say there. Okay. Okay. So by the uniform boundedness principle, there is a G delta set. Let's call that delta G0. Right? I'm calling G0 because this we are doing, we are evaluating at a point 0. So let's take 0. Okay. I mean, anyway, don't bother. So TNF is defined like this. So there is a G delta set such that G0 such that I mean G0 is a G delta set such that supremum of this is infinite for all f in G0. Okay, that's what the uniform modulus principle tells you. So for every function in G0, this happens. TNF, supremum over n, TNF is infinity, which basically means that for all f in G0, the Fourier series diverges at x equal to 0, right? Because TNF by definition is the partial sum of f, right? TNF is by definition the partial sum, the nth partial sum of f evaluated at 0. So when you say this is infinity, you basically mean this supremum of n, I mean n, supremum over n basically means the Fourier series. The Fourier series of f evaluated at 0 is diverging. That's what this means. Which means for every element of this set G0, the Fourier series of f diverges at x equal to 0. So this x equal to 0, just as one could repeat this argument for any x in minus pi to pi. So for every, right, so note that this result is true for any x in minus pi to pi, though we started with 0 here, it's true for any x from minus pi to pi. So for each x in minus pi to pi, if you apply the same result as argument, I mean the same argument as above, you are going to get a G delta set, let's call it Gx, contained in this, such that the Fourier series of f for every f in Gx will diverge at x, right? So let's for simple, I mean just for understanding, let's take a countable subset of minus pi pi. Let's call that elements of that set as xi. So it's a countable subset of minus pi pi. And then you define your G to be intersection of, so for each xi, there is a gxi, G delta set gxi, and for every function in gxi, the Fourier series diverges at xi, right? So you take intersection of gxi, that is an countable intersection of G delta set, which is also a G delta set. So you have a G delta set G, and that is also dense because each of them is dense, each of gxi is a dense subset. So G is a dense G delta subset of C minus 1, and the Fourier series for Fourier series of every f in G diverge at all xi's, right? So this is the Fourier. So for all f in G and for all xi that you have chosen here, which is a countable collection, the Fourier series will diverge. Okay, and this set G that we have taken here cannot be a countable set by when we proved the bare category theorem. We had shown that for uh, any countable dense subset of a complete metric space with no isolated points cannot be a G delta set. So now in our situation, what we have is a G delta set. If that set, and we are in the complete metric space situation, because C minus pi pi is a Banach space, it has no isolated points. So if that G delta set was complete, it will contradict, and it's also a dense subset. So if it cannot be countable, if it was countable, then it cannot be a G delta set. So it violates this corollary, which is a consequence of the bare category theorem that we had shown, right? So what we have now is that the G that we have obtained, so the G that we have obtained is now a G delta set, which is dense, and it cannot be countable. So we actually have an uncountable collection of F for which the Fourier series diverges in a countable collection Xi, right? So that's a large set. Okay, so the set G cannot be countable because it is a dense G delta subset. So the corollary that I just showed you, if it was countable, it cannot be G delta or it cannot be dense. So this G is an uncountable collection of functions. So for every f in G, the Fourier series has to diverge. It's a big collection, and all these f, so an uncountable collection of f diverge at a countable collection of xi's that we have chosen here. So thus what we have shown is that there is actually a large collection of functions for which the Fourier series diverges on a large collection of points. Okay, so that's a good. So this is a very good application of the bare category theorem and uniform boundedness principle and so on. Okay, so which means that we have collection of functions for which the Fourier series need not converge. So even if you start with a function f, you write down its Fourier series, it need not always converge to the given function, and even converge at all. It may not even converge at all. So these things can happen. So with this we will stop. We'll continue in the next lecture to see more on this approximation theorem and approximation theory and so on. Thank you. Thanks a lot.